In this tutorial, we are going to design a simple blinking LED circuit for PCB layout. SCH-RND starts with a blank sheet created from a template. It has a title box with text filled in from the sheet attributes. Open the Preferences dialog to change the attributes of the sheet. After filling in attribute values, the title box is automatically updated. The file still has no name. We are naming it at first save. We are ready to place the symbols the circuit requires. Open the Library window. The easiest way to find a symbol is entering part of its name in the filter entry. This will narrow down the library tree to matching symbols. When a symbol name is clicked, the preview on the right side is updated and the symbol is loaded into the paste buffer. It can be rotated in the buffer using the hotkey EW. Placing the symbol to the sheet is a single click. It is good practice to place and arrange symbols on a 4K grid. Opening the library window has a hotkey too, WL. There may be different symbol variants available for different drawing styles. Filtering and preview help choosing the right one for the circuit. We continue and place 4 resistors, 2 capacitors, 2 NPN transistors and a battery. Next task is to arrange the symbols. They can be rotated and mirrored on the sheet. Simple drag and drop moves the object. There are different ways to select multiple objects. For example, using shift-click. When there's an active selection, drag and drop moves all selected objects. Once the overall placement is done, it's a good idea to save. Hotkey for saving the current sheet is FS. Clicking the wire icon in the toolbar activates the wire tool. Click at the starting point of the wire. The crosshair starts to drag a dogleg of 2 thick red lines. This indicates the 2 wires that would be drawn on the second click. The direction of the dogleg, or refraction as we'll call it in Ringdove, can be temporarily changed by holding down the Shift key while moving the mouse. On the second click, the proposed lines are created as wires, and the last endpoint is now the start point of the next wire segment. This makes it easy to draw a sequence of wire segments. Pressing Escape breaks the sequence, and the next click will be a new starting point. The blue dot at the top is a junction, which means crossing wires are connected. The green dot at the bottom is a connection, which indicates the wire makes a connection to the resistor's terminal. If you find yourself constantly pressing Shift, you may invert the default refraction using the slash key. Wires are normally horizontal and vertical, but occasionally we need diagonals. This is done by grabbing the end point of an existing wire line and moving it. Note, the line is not split at the junction. It's easiest to draw diagonals by starting from new short line segments. We don't get a junction at the crossing. A junction or connection is made only when an endpoint of a line meets another wire or terminal. Now that the wiring is done, it's time to save again. Connection indication is useful to see if a wire successfully connected to a terminal, but all the green dots may clutter the drawing. On the left side of the top window is Layer Cell, which allows selecting layer visibility. Connections have their own layer that can be turned off. Next, we need to fill in metadata. Component names, refdes, footprint, values for all symbols. Let's start by naming our symbols. The quickest way is pressing AA while hovering over the symbol. This opens the attribute editor for the symbol with the name attribute already selected. Click Set to accept the new value, then close the attribute editor. The process can be further optimised by using the keyboard more. The old name is already selected when a dialog opens. Simply typing the new name will overwrite it. Then Enter to accept it and Escape to close the attribute editor. For this tutorial, we are going to name all symbols this way. There are more efficient ways for dealing with many symbols. These will be discussed in a subsequent tutorial. Next, we are going to set values. This is the same process using AV for changing the value attribute. If you make a mistake, like changing the name instead of the value, you can undo using UU. That's pressing the U key twice. Next attribute to fill in is footprint. For the generic non-polarised parts, like resistors, it's as easy as filling in the attribute called footprint. The hotkey is AF. The footprint name needs to be looked up in the PCB Layout Tools library. With transistors, it's not enough to set the footprint. Different models have different pinouts, even if they are using the same footprint. The standard solution to this problem in SCH-RND is called DevMap. DevMap is a library of entries that create attributes in a generic symbol so it becomes suitable to represent a specific device. It is typically used to fill in the port map, which is the pinout, and often the footprint attribute as well. DevMap entries are usually named by the model and footprint. The hotkey to change the DevMap attribute is AD. It presents the DevMap library in a window very similar to the symbol library window. Our transistor for this circuit is 2N3904 in TO92. Click that entry and inspect the right side. It is going to set a footprint and a port map. Once it's accepted, autocompile triggers, and the new pinout appears. Base is pin 2 instead of pin 1. When there's a lot of dev maps in the library, it's best to use the filter. Entering the model will narrow it down to a few footprint variations. The same devmap method is used with LEDs so that the symbolic A and C terminals can be mapped onto footprint pin numbers. Our devmap is called LED5 for the 5mm LED. After the modification and autocompile, PCB footprint pin numbers show up instead of A and C. Revisiting our capacitors, we still have the P and N terminal names there. Since we've set an RCY for the footprint, we need to get symbolic terminal names mapped to that specific footprint's pin numbers. There's a dev map entry for that called pol RCY. Symbols usually have a few attributes printed around them. It's easy to get more of them printed. Right-click on the symbol, pick the attribute editor. Select the footprint attribute. And click the Floater button. This will create a floater text object that prints the value of the footprint attribute. Being a floater, it can be moved, rotated, mirrored, so you can tune its placement. Next, we are going to name our networks. It's good practice to name all important networks. It makes laying out the board easier. Hover over a wire and press AA to name the associated net. The process is the same as with naming symbols. Also click on the floater to get the name printed on the sheet. The net name is rarely printed at the right spot when the floater is created, but it can be moved. There is one symbol we did not handle. The battery. It is a special case, because we want to have it on a generic connector footprint, but it is a polarised part with P and N for terminal names. The easiest way to handle this is a custom port map. Details will be covered in a subsequent video. The drawing we worked on so far is called the concrete model. There is an abstract model in the background, which is the real meaning of the drawing. For example, the concrete model has symbolic names N and P for some of the terminals, while the abstract model for the PCB workflow will contain the final footprint pin numbers. Compilation transforms the concrete model into the abstract model. The net list we need for the PCB layout is generated from the abstract model. Open the abstract model window to inspect the abstract model. The abstract model is usually available because autocompile is normally enabled. The abstract model consists of components and networks. You can browse through them and look at their attributes. It is good practice to verify the abstract model before generating any output. For example, a non-net2 is a network with a bunch of terminals connected, a network we forgot to name. Since LED 1A, the anode of our LED, is connected to it, this must be the positive power rail. It is not obvious because at the moment PCB pin numbers are printed on the sheet. This depends on the view, which can be changed to RAW. In the RAW view, the compiler does not do any transformation to the terminal names. Now that we confirmed the network, let's name it VCC. As soon as the compiler finishes, the abstract model window is updated. The other important net we did not name is ground. The rest of the nets are unimportant and can be left with their automatically assigned net name. Switch the view back to PCB. This will matter for the export. Invoke the export dialog from the File menu. Then select the TDAX format for exporting. Fill in the output file name. When the view field is left empty, the current view is used when compiling for the export. Our current view is PCB, so the export will contain the PCB footprint pin numbers. Click the Export button to get the file written. It is also possible to make graphical exports, for example in the PostScript format, using a similar method.